Good morning, student. Welcome to the physics class. In this session, we will discuss the chapter number 7 of class 12, and the name is chapter is moving charges and magnetism. But the first part of this chapter we will already discussed, and here we will discuss the second part of this chapter, and the rest topic all are completed in this part. So we will start the last topic, and the last topic was of this chapter, Ampere Circuital law. So student, from this topic we start here, and the topic is Ampere Circuital law. This is important chapter and this is important topic. So according to this law, the line integral the line integral of the magnetic field B around any closed path is equal to the mu naught times of the total current I threading through the area enclosed by the path, that is integral B into dl is equal to mu naught times of I. Now I want to explain. If we take a wire of infinite length, then the magnetic field produced due to the small length of a wire, that means line integral, will be equal to the mu naught times of the total current flowing in that wire. This is the statement of Ampere's circuital law. Now, the proving of this law is, first of all, we take a wire XY of infinite length, and I is the current which is flowing in this wire, and the circular portion shows the direction of magnetic field which is just produced around the wire. Then take a point small dl on the circular loop, and at that point the magnetic field is B is equal to mu naught upon 2 pi I upon R. We know that because this is the derivation which is already discussed by us. Now, the magnetic field due to line integral, that means the small length of a wire, will be line integral B into dl is equal to integral of B into dl. Now, B is a constant, that means take outside, so B into integral dl. Now, on putting the value of B, we get mu naught upon 2 pi I upon R, and integral dl is equal to 2 pi R, because dl is the small length, and on integrating the small length we get the total length, and here the total length means the circumference of a circular loop, which will be 2 pi R. So on putting the value we get finally mu naught I. So this is the statement, the line integral of magnetic field around the wire will be equal to the mu naught times of the total current threading in the wire. Now student, we will discuss here the applications of Ampere circuital law. There are many applications of Ampere circuital law, in which the first application is magnetic field of a long straight thin wire. If we have a long straight thin wire, then we can find the magnetic field due to Ampere circuital law. So we know that integral B into dl equals to mu naught times of I. So here we can write integral B into dl equals to mu naught integral B into dl, that means B into 2 pi R. So from this formula we can find the value of B. B is the magnetic field due to thin wire. It will be mu naught upon 2 pi I into small r. Now the second application is magnetic field of a long straight solenoid. So first of all, I want to describe what is the meaning of solenoid. Solenoid is a construction which is made by turning a number of turns of an insulated copper wire on a cardboard or china clay. And in the case of a solenoid, length is always greater than, much more greater than breadth. So here A, B, C, D in the figure is a solenoid where length is very high and breadth is very small. So the total magnetic field due to the small portion of a solenoid is considered according to Ampere's circuital law, and it will be integral B into dl is equal to mu naught times of total current. This is a statement of Ampere's circuital law. Now applying this law on the wire and all the parts of a wire, we get mu naught into dl integral is equal to A to B integral B into dl plus B to C integral B into dl plus integral C to D B into dl and integral D to A B into dl. Here integral B into dl is equal to integral B into dl, where limits B to C and D to A both are equal. It will be cancel out, that means the value will be 0, and theta is 90 degree, that means cos theta equals to 90 degree, that means integral C to dB into dl is equal to 0 because cos 90 equals to 0. So the total magnetic field B into dl will be equal to integral A to B B into dl, that means B into L. So on solving we get the value B into x, where x is the length. So if this contain a number of turns, then the total current I will be equal to n into x into I naught. So putting the value, we get B into x equals to mu naught n into x into I naught, that means magnetic field B is equal to mu naught n into I naught. Now magnetic field of a toroidal solenoid. Toroidal solenoid means endless solenoid. Means in this case the number of turns are very high, very much. That means they can be endless turns. So magnetic field inside the core of a toroidal. The toroidal is a construction which is made by a number of turns of insulated copper wire again and again, and it is a circular loop. So first of all we have to find the magnetic field inside the core of a toroidal. So in the case of core of a toroidal, that means inside the center. So in this case B into dl integral equals to mu naught times of I, and on putting the value we get B integral B into dl is equal to B into 2 pi A, where 2 pi A is the circumference for a one round of a solenoid. If number of turns are capital N, the total current will be I is equal to N into I naught, where I naught is the current flowing in one turn, or you can say that in one circular portion, and total number of turns are N, that means the total current in the whole toroidal will be I. So the final formula, B is equal to mu naught upon 2 N I naught upon A, and if N is the number of turns per unit length of the solenoid toroidal, then we can put small n equals to capital N by 2 pi A, and by putting B equals to mu naught N I naught. This is the required formula of the toroid. Now student, we will discuss here force on a moving charge in a uniform magnetic field. Definition of B means magnetic field, and you can say that here we will discuss Lorentz force. So if we take a current carrying wire in a magnetic field, then the force acting on that wire will be equal to Q into V into B. That means it is equal to the product of three terms: charge, magnetic field, and V is the velocity by which it moves in any one direction. Now student, it can be also written as F is equal to QVB sine theta. So if theta is equal to 90 degree, then the magnetic field will be maximum, and this force is said to be Lorentz force. F maximum equals to QVB. Now still we will discuss here units of magnetic field. So we know that B is equal to F upon QV sine theta. So putting the units of all the physical quantities, we get Newton inverse, Newton, Ampere inverse, and meter inverse. So Newton into area inverse, meter inverse. This is the unit of magnetic field. And one another unit is Tesla. 1 Tesla is equal to 1 Newton per A inverse M inverse. and it is also written as 1 Weber per meter square. Now the dimension of magnetic field is m l minus 2 sorry m t minus 2 a minus 1. Motion of a charged particle in a uniform magnetic field. Here we will discuss the motion of a charged particle. That means when any charged particle is placed in a magnetic field, then which types of waves, yeah, what is the path of the charged particle when it moves. So when V is perpendicular to B, that means the motion of a charged particle is perpendicular to the magnetic field. In this case, F is equal to QV cross B. So, so we know that F is equal to QVB. Here F is the Lorentz force which is working on a charged particle which is placed in the magnetic field. And we also know that when any charged particle moves on a circular path, then a force is working on the center which is known as centripetal force. In this case we equating and we get small r is equal to mv upon qb. So this is the radius of a path, radius of a motion of a path where charged particle moves. Now we can also find the kinetic energy of a charged particle. K is equal to half mv square. So it will be v is equal to under root 2 k upon m, where v is the velocity of charged particle which is moving in a magnetic field. Clear it? So on putting this value, we can find the radius of a path which is covered by charged particle. Small r equals to under root 2 mk upon qv, and we know that k is equal to qv. So putting this value, r equals to 1 upon b under root 2 mv upon q. If we want the find a time period for the circulation of charged particle in a circular path, then t is equal to 2 pi small m upon qv, and the number of turns which is taken by the charged particle is 1 upon capital T, that means qv upon 2 pi m. Now student, we will discuss here motion of a charged particle in a combined electric and magnetic field. That means if any charged particle is moving in magnetic field as well as electric field, means both field at the same time, then the Lorentz force working on that particle will be F is equal to Q times of E plus V into V. That means here we use magnetic field, magnetic force Q, VVV, and electric field is QE. If in any condition both fields are equal, that means QE is equal to QVB, in that case V is equal to E by B. That means the velocity of charged particle will be the ratio of electric field to the magnetic field. Now student, we will discuss here cyclotron. It is also an important theoretical topic which is generally asked in a small portion. That means you can say that it is a short answer type question. So you have to understand what is the construction and what is the formula of this electrical instrument. So cyclotron was devised by a scientist Lawrence in 1932, and this is used for a positively charged particle like protons and neutrons to very high energy, so that they could be used to disintegration experiment. Means generally this instrument is used for accelerating a very high energy charged particles like electrons, like protons, neutrons, etc. Construction. In this instrument there are two semicircular portion which is known as D's, and when we placed a charged particle between two D's with the help of a strong potential difference, then the charged particle moving in a circular portion like this with very speed and go to the target and strike the target with very energy and melt it. This is the construction, theory and working. So as we know that when a charged particle moving on a circular path, then the radius of a circular path will be small r is equal to mv upon qv, and small t means time is pi m upon qv. So with the help of this concept, we can find the path of a charged particle which is covered by accelerating particles by providing a lot of energy. Now student, we'll discuss here achievement of resonant condition. So how can we achieve a resonance condition in the cyclotron? So if v mu naught will be equal to mu, then the condition is said to be resonance, and in this condition mu naught is equal to qv upon 2 pi m, where nu naught is the frequency of the applied potential difference and v is the frequency of a circuit. That means you can say that it is a original frequency. Limitations. What are the limitations of cyclotron? Cyclotron cannot accelerate the particles to the velocity as high as compared to light. First. Second limitation is cannot accelerate uncharged particle. That means if we use uncharged particle, then it cannot be accelerated. Third is cannot accelerate electrons due to very small mass and acquiring very high space, means this speeds. That means it is not used for the electrons. Energy, kinetic energy of a charged particle accelerating in a cyclotron. So in the case of a cyclotron, the kinetic energy of a charged particle will be k is equal to half mv square is equal to q square v square r square upon 2m. Now student, we discuss here force on a current carrying conductor placed in a uniform magnetic field. In this topic we will discuss some rules. First rule is right hand palm rule number 2. According to this rule, if we adjust our right hand palm in such a way that the thumb shows the direction of current and the finger shows the direction of magnetic field at a point where we have to find the magnetic field. So the palm shows a perpendicular direction where the point is placed, where we have to find the magnetic field. So this is the right hand palm rule. Now student, Fleming's left hand rule. It is also important. If we adjust our left hand rule in such a way that the forefinger, that means this finger is known as forefinger. Forefinger shows the direction of magnetic field, thumb shows the direction of force, and you can say that the middle finger shows the direction of current, forefinger shows the direction of magnetic field, then thumb shows the direction of magnetic force. Clear it? So this is the Fleming's left hand rule. Now student, expression for the force. If we take a conductor in the magnetic field placed and the length of conductor is small l and current I is flowing that conductor, where the direction of electron is just opposite to the direction of current and the electron is moving with drift velocity vd, then we know that Lorentz force F is equal to qvv sin theta, and we can also write it F dash equals to evdv sin theta in the terms of drift velocity. And if capital N is the total number of terms, then we can write it capital N equals to small n, A is the area of cross section and L is the length of a wire, that means total volume. So here total or net force F will be equal to F dash into capital N. Now it will be equal to finally NE AVD B into L into sin theta. So we can write it F equals to IBL sin theta, and here we use sin theta, that means sin theta is generally used for the cross product. So in the case of vector, we can write it V is equal to IBL. So this is the required formula of a charged conductor which is placed in the magnetic field. Now students, we will discuss here force between two parallel current carrying conductor definitions. So if we take two conductors which are parallel to each other, then the force is working in two different ways. If the direction of current in both two conductors are same, that means same direction, then the force is working between these two conductors will be attractive, that means both force attracted to each other. And when the direction of current is just opposite, then the repulsive force is take place. And the expression for force is, we know that the expression for magnetic field is V1 is equal to mu naught 2 pi I1 upon R due to the first wire, and force F is equal to I2 V1 L sine 90 degree, because the angle is 90 degree, because both are perpendicular to each other. Now, F upon L, that means force per unit length of a wire, will be equal to mu naught upon 2 pi I1 I2 upon R, where I1 I2 are the current which is flowing in both two wires, and R is the distance between two wires. Now, so student, these are the topics which was discussed by me in this part, and this chapter is very important because from this chapter at least two questions should be asked in the board examination, and this chapter is also important according to competitive examination because number of two questions is generally asked in the examination. So keep watching the video and do as much as possible questions, and study very well the concept and videos and topics of this chapter. So do as well as possible. Okay students, thank you very much.